So again, right, this one, key thing is it is normally distributed. Right, the question for the individual score has to tell us the score is normally distributed, right, or a random variable is normally distributed. If not, then these type of questions we cannot do. Like the empirical rule before, right? So if you want to use the empirical rule, the question has to tell us the random variable is normally distributed. Right? If we don't know the distribution, then the question says empirical rule. That means we cannot do the question. Or we can say, well, the empirical rule does not apply since the distribution is unknown. Right, and this key here, saying the score is normally distributed, find the percentage of students satisfy the requirement, which means it has minimum of 700. So asking for the probability of x is bigger than or equal to 700. Given that x is normally distributed with a mean of 998 and standard deviation of 202. Right? X is the random variable of the SAT score. It's normally distributed with mean of 998 and standard deviation of 202. Asking for x to be greater than 700 will be the accepted minimum. Right, lower ladder cutting. So we have the density of x, which is 700 is the value we're looking for. And minimum of 700 means 700 or more for the SAT score will be accepted by it, right? Regardless of other things. We just see it's normally distributed. That is what it is. And that is the x. Right? To find the z-score, which is 700 minus 998 over 202. Right, so two steps, find the difference of numerator. 700 minus 998, that's negative 298. Divide by 202, that's have a long decimal, negative 1.475 and so on. And we will keep the z-score to be always have 2 digits of decimal. Even though the third digit is 5, we'll be rounding it to get negative 1.48, right? Because negative 1.475 is closer to 1.48. That is the reason called rounding, right? Rounding to the nearest digit, in this case near hundreds, which the thousands place 5 is closer to 10 compared to 0, so we round it up to negative 1.48. So the density curve, 0 in the middle, we don't have to draw that all the time. Negative 1.48 is on the left. Right, so it's finding for the z density or finding for the standard normal distribution at least negative 1.48. Right, if you use 1.47, then you get a different probability, right? So it is very important that you will get the correct z-score. Right, Right, and this probability will be 1 minus the phi value of negative 1.48. This is negative. So we go to the negative side of the z-score. We go down to negative 1.4 in the column and go right to find 0.08 on the row. Then the intersection value will be what they're looking for, negative 1.48 for the phi. That's 0.0694. Right. The table of negative z-score is negative 1.48. We go to negative 1.4, we go to 0.08 to find the intersection. Then when we subtract using the calculator, that will be in the net 0.9306. Right, about 93% will be accepted. Right, so that is the z-score. We'll see more examples later on, but the most important thing is the question has to tell us some random variable is normally distributed or follows a normal distribution, Should we provide us the mean and standard deviation, and then maybe asking us for some other things, right? Such as the body of the question, right? Say minimum requirement is also 700, and asking for the percentage satisfying the requirement, or maybe asking the percentage of students not satisfy the requirement. We'll be asking for similar but opposite thing, right? If score is less than 700, that will be not satisfied by the requirement, and that is what it is. Then we'll move on to the next topic about the sampling distribution, and so on the central limit theory. Right, the sampling distribution is the first thing to be discussed. And then we'll go to the sampling distribution. Then we'll go to the central limit theory. In this case, we're doing the sampling distribution of the sample mean. It is the sample mean, the probability distribution basically. is a probability distribution of the sample mean with all sample have the same size. That is a probability distribution. The random variable is the sample mean of all sample have the same size. Which means if we have a population, then we could find out the sample of size 2, maybe size 3 or size 4, then we have the sample mean of the size 2. Then we can build a probability distribution, assuming to get, of course, to get each sample be equally likely. Then from that idea we can get the probability distribution. So we can see some small example. That's assuming we have a population of 1 to 3. Then what we're doing is we could pick up two numbers at a time to form a sample. That the formation of the sample could be replaced. Which means with replacement or could be repeated, right? So at the same time that is could be repeated. If we pick one by one, that's to form the sample which is replacement is allowed, right? Which from the number 1, 2, 3, we can get a sample of 1, 1, 1, 2, 1, and 3. We can get the first is 2, second is 1, 2 and 2, 2 and 3. We can get 3, 1, 3, 2, and 3, 3. Right, that's the sample. Therefore, the mean of each sample, which the distribution is of the sample mean, so we need to find the mean of the sample. Right, that's what we do with sampling. We get from the population, we get a sample of size 2. Right, and from there we can get our sample mean. The first have a mean of 1, 1.5, 2, 1.5, 2, 2.5, 2, 2.5, and 3. The sample of size 2, we can just add the sample together and divide by 2, right, to get the mean. So that is the sample mean of the group from all the possible cases of 9 cases. Therefore, we can build a probability distribution of the sample mean. We have sample mean of 1, we have sample mean of 1.5, of 2, 2.5, and 3. That's all the cases of the sample mean. And with probability to have 1, that's only one case out of 9 possible cases. For 1.5, we have 2 cases out of 9 cases. And for the mean to be 2, that's 3 over 9. For the sample mean to be 2.5, that is 2 cases, and one case only for the sample of 3. Right, so that is the probability distribution of sample mean with all sample that have size 2 from the population. Right, so that is what it means. Then of course, from the population, we can find the population mean, we can find the population standard deviation. You can try that. I use the formula we discussed before. From the probability distribution here, we can find the mean of the sample mean. We can find the standard deviation of the sample mean of this probability distribution. And finally, if you try that, right, the probability distribution to find mean and standard deviation, also we have formula to do them, right? Then after that, we'll find out they are related. And you could try that. You can also find the relationship that the mean from the probability distribution of the sample mean is actually same as the mean from the original population, mean of the original population, and the standard deviation of the new sample mean we had done from the sampling distribution equals to or variance equals to the variance of the population divided by n. That is the case that's generally correct. We can prove that by other way, but from the sample we can see that also holds. You can try this to find the population mean of 1, 2, 3 and to find the population mean of the distribution listed before. You can find out this relationship actually holds. That is the sampling distribution. To be clear, that is true for all the sampling distribution to be hold. Then from the sampling distribution, it is somehow a little clear what we are doing. Then we can go to the thing called central limit theorem. What does central limit theorem say? The random variable x has a distribution with mean of mu and variance sigma squared. Simple random sample was the sample we built it before. Repeated aloud and all the cases are considered to have same likelihood to be chosen. then the simple random sample of size n has a sample mean can be approximated as a normal distribution. As n increases, as the sample size increases. Of course, the distribution before, of course, is not normal, right? We have seen the population of 1 to 3 that will look not that much normal, but when we graph it, we may see something maybe looks like. Right, but actually, the theorem called central limit theorem says that the sample mean of the simple random sample of size n pulling out from the population can be approximated as a normal distribution as n increases. That's the worst case scenario, right? That is the worst case. The better case is if we already know the x is normally distributed, then whichever the n is, the sampling distribution will have a sample mean is normal distribution, actually. If we don't know the distribution, but n is certainly a large number, then the sample mean will be a normal distribution also. So some different book states different thing for how large the n should be. We have originally the distribution of x was mu and sigma square for mean and variance. And we had seen for the sampling distribution, the sample mean will have mean of the same as the population mean, and variance will be variance square over n. And that we don't know the distribution of that. And as n increases, that will go into a normal distribution, approximated to a normal distribution. In other words, the mean of the sample mean is equal to mu, and the standard deviation of the sample mean, we're taking square roots of that, that will be standard deviation of the original over square root of n. That is what the central limit theorem states. Right, so which means the sample size of n could approximate the sample mean of the sample to get into a normal distribution with the mean of the sample mean equal to the original population mean and standard deviation of the sample mean equal to the original standard deviation over the radical n. Of course, depending on the size of n, the variance or the standard deviation is different. If we don't know this distribution, n to be required as large number, then the sample mean will be normal. If the distribution originally of the random variable is normal distribution, then no matter what n is, right, how large n is, that sample mean is follow a normal distribution. So that is central limit theorem. Right, so some rules over there. So as we mentioned, if the population is normal, then the distribution of sample mean with any size n is a normal distribution. Or follows a normal distribution. That sampling distribution or sample mean basically is discrete distribution, but that follows a normal distribution anyway. Approximated, better wording, but actually it is normal. Doesn't have additional requirement. The key thing is, or the more important thing is, for any size of n, right? Doesn't matter what it is. Well, the population, if it's not normal but n is large enough, we have seen in the central limit theorem states, right, that can be approximated as normal distribution as n increases, right, for any distribution of x. That the population is not normal, but as n increases in our book, saying is n bigger than 30, right, especially n bigger than 30, then the distribution of sample mean could be approximated as normal distribution. And if the population is not normal and n is small, right? But still, some other book maybe states bigger than or equal to 30. That is depending on the author of the book, what he or she choose. But the book we use from our school, say n bigger than 30. Some other school may be saying, oh well, 30 is too small, too big, maybe 25 is good, maybe 40 will be a good number to state it's large enough, then everything is acceptable depending on different cases. Our book and what we are using here is saying n to be bigger than 30, then could be approximated. Right, so if we don't know the population and our given sample size is small, in other words less than or equal to 30, that distribution of the sample mean cannot be approximated as a normal distribution, which means doesn't satisfy the condition from the central limit theorem that n is large enough. Right, so those are the rules. If the population given is normal, then we're done, right? Any size is good. Population doesn't mention, but size is large. In our case, large means greater than 30. That could be approximated by normal distribution. We still could do the problem. other cases, not normal and sample size is small, nothing we can do. Alright. So let's see the example involving that. Alright, the ski gondola to be safety, right? The maximum capacity for 12 people is about 2,004 pounds, in average 167 pounds per person. Right, then also we are in the worst case that all men are on the ski gondola. The worst case scenario is all men on the ski gondola, which means the weight is higher. And what we know that the man's weight is normally distributed. The mean is 172 pounds, the standard deviation is 29 pounds. Right, our first question. To ask, well, find the probability that one man is heavier than 167 pounds. Right, to solve for it, we had seen much example already, right? Given the man's weight is normal distribution, we're looking for one man is heavier than 167 pounds. That we know X is the man's weight, is normally distributed. 172 pounds and 29 is the standard deviation. Right, the density of X is 172 in the middle. 167 may be just a little lower than 172, and that is the area we're looking for. We're looking for the probability of mass is bigger than 167 for one man. That is the probability looking for, and that is the density. Then the standard deviation and mean is given, so we can looking for the z-score is the value looking for 167 minus 172 for the mean, and divided by the standard deviation of 29. We can use calculator to find the score. That's negative 0.17. So actually looking for the probability of z bigger than negative 0.17. We'll be more closer to the middle, right? The middle is 0, maybe just a little left, 0.17. The probability one man is heavier than the 167. That means looking for the probability of z-score greater than negative 0.17. Every time we're looking for the area to the right, we use 1 minus the phi of z-score. Now we go to the negative z-score side, go to negative 0.1. It's almost the bottom, 0.17. Right, the third from the right, which is 0.4325. Like 0.4325, and we get the probability will be 0.5675. Right, that is for individual. One person, one man is heavier than 167. So that's the first part of this question. Find the probability that one man is heavier. Find the probability that in the question the ski gondola, right, needs 12 people to fit in. Find the probability that 12 men have an average weight heavier than 167 pounds. And we know that's looking for the sample mean, right? The average weight is the sample mean higher than 167 pounds. Right, the sample mean bigger than that. For the sample mean is normally distributed because the original high mass weight is normally distributed. Right? Therefore, the sample mean is normal distributed, is follow normal distribution, And from sampling distribution, the mean of the sample mean follows the same as the population mean, 172, and the standard deviation of the sample mean is the original population standard deviation of the radical of n. And the more digits we keep will be better or more accurate answer. Since z-score need to keep only 2 digits decimal, maybe standard deviation keep 4 digits will be good idea. Of course, the more digits the better. The less digits, like 3 digits of decimal, also is okay, but try not to keep less than 2 digits, right? That will be more or less dangerous. So calculate out the z-score. Is the sample mean of 467 minus the mean of the sample mean divided by the standard deviation of the sample mean, because the sample mean follows the sampling distribution. That sampling distribution has a mean and standard deviation as we have found already. 167 minus 172 divided by 8.3716. Instead of the original we had last time was 29. Well, in this case, it will be a little bigger. That's negative 0.60. So for the z-score, we are looking for the probability convert to standard normal distribution, negative 0.60 and higher. Like that, here's 1 minus the table value of negative 0.60. Since it's bigger than, then for the table value, we go inside the negative side and we'll find out the value is 0.2743. And the final answer is 0.7257. So this one is the involving sampling distribution to find actually the sample mean or the average